Let's take a look at Lesson 9, Activity 3, Question 5. We're given this picture of a polygon, and we're given that line segment BC is congruent to line segment CD, and that AC bisects angle BCD, and we're asked to prove that the two triangles, triangle ABC and ADC, are congruent. Now, this proof is partially filled in for us, and we're asked to complete the statements and what is missing. So we've got something missing from line 3, which has an X placed in, and something missing from line 4, which has a Y placed in. And we're asked to select the items for X and Y that will make this proof complete. Still, let's take a look at this proof starting from the beginning. So, as always, if we know our givens, that's the first thing we want to take note of. So we were given that line segment BC was congruent to CD, and so you see that's the first thing that appears in our statements. Same thing with the next given, line segment AC bisects angle BCD. And so that's our second given. So what can we make of this information that will allow us to prove that triangle ABC is congruent to triangle ADC? Well, in this case, because there's probably and there is often more than one way to go about a proof. From their setup in this problem, we know that they're going for a certain way of solution. And by that I mean if I look at the final line, line 5, when it is finally claimed that the two triangles are congruent, the reason is the side angle side congruence postulate. Side angle side congruence. So I know that this is going to involve showing congruence of two sides, a congruence of two sets of sides, of corresponding sides, and then a congruence of one set of corresponding angles. So I know that's my aim, and I'm just thinking about how to get there. Now, on line 3, they claim that angle 1 is congruent to something based on the definition of bisect. And if we take a look, we were told that AC is a bisector for BCD, so BCD. Think about the definition of bisect. What does it mean? And hopefully by now it's somewhat of a reflex for you to know that if something bisects an angle, then it separates the angle into two angles of equal measure. So if AC is a bisector for this angle BCD, then angle 1 must be congruent to angle 2, based on the definition of bisect. So notice by proving through the definition of bisect that these two angles are congruent, we now know that these two angles are congruent to one another. And notice we've already proven a side congruence because of side CD and side CB being congruent to one another. And we've proven an angle congruence. We've got an angle. Now we have a remaining side to prove. And let's take a moment and kind of zoom out here and make sure we understand what triangles we're talking about. So we've got triangle ABC, which would be, and I'll just kind of gently shade it in here, this triangle formed up here, and then triangle ADC, which would be this triangle formed down here. So I know that CD is congruent to CB. I know that angle 1 is congruent to angle 2. What's the last thing that it makes sense we would try to prove? Well, they share, both of these triangles are formed with line segment AC. So if they're formed with the same line segment, it would make sense that it must be of equal measure, right? But we have to know the right wording and the right way to claim this. So I'm able to claim that line segment AC is congruent to itself, and that makes sense, right? Any line segment or any angle is probably equal to itself. It's kind of like reflecting something in a mirror, right? But what is the proper name of the reason I can claim this? It is the reflexive property. The reflexive, and I'm not going to write it out fully, the reflexive property of congruence. And that just tells me that a line segment is congruent to itself. So if this line segment, I'll give it 3 tick marks to denote congruence, is congruent to itself, I now have a side, an angle, and a side proven on these triangles as far as congruence goes, and this angle is an included angle, which means now by the side-angle-side congruence postulate, I know that triangle ABC is indeed congruent to triangle ADC.